Hola, thank you Armand and Andre for the presentation. Before the talk, this morning I was reading the title of the presentation and I didn't feel comfortable because probably if I asked to some of you if there is something beyond Smalltalk code, some will say no. There is nothing beyond Smalltalk code, so everything is Smalltalk code. And I will say, probably yes, you're right. So I don't feel comfortable. And I wanted to modify the title, and the idea of this presentation is about that. About writing something, thinking, and probably modifying this thing that you do. So, at the end, everything is Smalltalk code, and we want to characterize which kind of Smalltalk code we do want, and in a particular problem, which is the project that we do work. Some of you know we are writing a Smalltalk virtual machine written in Smalltalk. So we want Smalltalk code for this virtual machine, and something beyond, if there are. So.
Okay. There we have an image of what a common Smalltalk programmer, what he does every day. He opens an image, he starts working, he creates objects, he sends messages.
Sorry.
Okay. So this is what we are working on, which is a bit different. We have an image running and we are coding a VM in Smalltalk. We want to show you some of the things that we face every day when writing a VM in Smalltalk. So,
for this project, we started with a just-in-time compiler. We wrote some cheater that was bit compatible with some other implementation. Then, using the same framework, we wrote some garbage collector and a few of them, and we start playing. And then we have to put all the things together to have a virtual machine and to have a Smalltalk environment. So we want a robust, clear, evolving Smalltalk. And this is the thing that I wanted to say when I say something more than just Smalltalk code. It's not like, okay, I have the VM written using Smalltalk syntax and I can go to sleep. No, we want that. And that is Smalltalk. Okay. So when we say roast.
Okay. When we start talking about roast, we would like to think a bit what we mean with a robust VM. Of course, we want a VM in which we can trust, a VM that doesn't crash, but also we want a VM that can create a lot of objects. There are different kinds of bugs. We want to avoid having bugs in our VM, but we are also depending on another VM, so we have to think in robustness in both sides, in our VM and the one we are working with.
Yeah, a key feature of this talk is that we are going to show small pieces of code, small, just to tell you that you can do the thing that we say that we declare that is desirable in a project that is kind of hard to implement, like a virtual machine. So everything will be explained with the Smalltalk code.
The first thing we wanted to talk about this is something we call the small pointers. If you look at this number is an address of an object, but in a VM, in our VM, every object is aligned to 4 bytes. So that means that the least significant bytes, the 2 least significant bytes are 0. And on the other hand, if you work with addresses below 2 gigabytes, you have a 0 in the most significant. But what happens if you want to do some arithmetic with this integer in Smalltalk and you want to convert that into a small integer? Because, for example, in the garbage collector, you have to calculate where is going to be the next object, for example. So you have to take the address and add to it something. So you want to do some arithmetic, but when you look at the small integer you get, it has 1 in the most significant bit, but we are working with a 2 complements arithmetic, so this is a negative number. So you can't work with this address using a small integer if you don't do anything.
So we create the small pointer.
The idea we got was, okay, why don't we take one of these 2 bits that are always 0, because the object is aligned, and use it to tag the address. Okay, so this is a bit of a mixture of an address and a small integer. Actually, if you look from the Smalltalk side, it's half the address. It represents half the number. With this, we can get 1 bit more for address representation, so we can get addresses double the size.
Yeah. We are still moving the problem to some other place. Like, okay, we can address some addresses, but at the moment we don't care about that, and we are happy with that. So this is the implementation of the primitives. We call it under primitive, and this under primitive transform an object to a small pointer. It's a small implementation, so we can do that in the garbage collector to an space. We can ask if an object belongs to that space, and we use as pointer. We will not have the problem with negative numbers. To make it easier, we can extend the literals to use the new pointer literal. And those problems arise when you do testing. And we have a lot of tests, like 5,000 tests. We found some bugs in our Smalltalk code. And we have some code to, you can ask to a space to shallow copy an object. Actually, the space is responsible for shallow copy the object. We have some subtleness. When you copy an object and the object belongs to the remember set, the remember set is something used for a generational garbage collector. The object remember that it wasn't the remember set, but probably the remember set is no longer. When you create a copy, the copy is not in the remember set. The original object were in the remember set.
Actually, it's used mostly for when you do a full garbage collection. So the remember set disappears after the full garbage collection.
Yeah. But the thing is that the new copy object is not in the remember set. So we have to add that line. And it was hard to detect that we missed that line, because it was in a very critical situation, very uncommon, etc.
You have to think that to find that line, you have to first understand that what was happening below after GC, the object saw that it was in the remember set. So after the next GC, you wouldn't see that in the next CC, the garbage collector will think that the object has already been traced when it's not. So its pointers may or may not be collected. So maybe then, when accessing these pointers, you will get maybe a crash or an error.
And using the test allow us to detect bugs in the implementation of the host VM, the VM that we are using because we can't use our VM for all the things, so we use another VM. We found some bugs. This is one. There is something in red in a new byte object using. A really subtle bug. It happens in a situation really uncommon when some object doesn't fit in some space, but it crashed, which is not root. So we are happy that we can find those bugs and understand, which is very important.
And try to avoid them in our VM.
Yeah. So, to make clear code is a process that we try to do all the time. It's not only when you write new code, but also when you just go around and see your code and say, okay, probably I can modify that. And we just put some examples, and it was strange, but when we create this presentation, we feel a lot of enhancement when we say, okay, we have to modify that, or I don't understand that method completely, probably we have to reorder that thing or create that name, etc. And I think this is a process, a continuous process, and a continuous process means a lot of work. People working, we are working, and we have to think about that when we say, okay, a continuous process of modifying things. Okay, that's important for us. And okay, we have a living system. We have everything is modifying, and our VM is not any longer decoupled to the image. So when you modify things in the image, in this example, but the compile method changed its instance variables. In a typical VM, it's like neutral, because if you don't change the class shape, everything is like transparent and everything works. But we have to take those changes and apply to the jitter or the. This is the process that create the dynamic link libraries. Also, if you stop using strings and use a pool dictionary, or this example, if you change the symbol that used to create association, you have to modify the virtual machine. And this is like, okay, it's hard, but it has a really good side, which is that the virtual machine benefits from the changes in the images. And I think that's very important. And it's like a consequence, a desirable consequence of a living system. And also, we want more Smalltalk code. That's important.
Yeah. And you could ask, okay, you want more Smalltalk code, what do you mean with that? We are calling the VM, which is most of the time not possibly modified. So we want to explore that idea. We don't know exactly what is to do more in Smalltalk. We are exploring each day. Here are some things that we are going to show that we found, but there can be more. For example, we asked ourselves about the primitives. The primitives are written in the VM, so you can't modify them. And we asked ourselves, how can we code the primitives in Smalltalk. What would that involve? What would that include? And okay, so we ask, okay, for example, add primitive. It's a small primitive, very short. So how do you call this primitive? What does the primitive add have to do? Well, it has to do some bounds checking. You have to be sure that you are accessing a slot that is inside the object, not before, not after. These are the typical things you do in a primitive. But then, after you do that, you just access the memory, okay? So the code of the app is bound checking and then accessing the position in memory. It's just that. It's only that. That's a result we got when we actually wrote the primitive, okay? So we are going to show some more examples. For example, longer object. It's a single primitive. You have to get along and you get past an offset. So again, you have to do bounds checking. You have to assure that you are accessing inside the object. But after that, the only thing you have to do is get the parts of the object and assemble them, because you have to take care that, for example, the long is signed and in the memory you may have something that is not, or manipulated is. But it's simple arithmetic. Okay. The last one we are going to show is value, which when I started working on this, I thought it would be a really hard to call primitive. And when we did that, we saw that it's a bit of the same. Bounds checking, you have to check that you have the same argument count. That if the primitive is value, you don't have any argument, so you have to check that the sender didn't send any argument. Then you have to look at the code, look if it's nativized. If it's not, you have to nativize the code, the bytecodes. So this is what we are doing. After that, you have the native code, and in the native code you have a block table, which indexes all blocks in this method. So you have to get this table and get the block, the corresponding block to execute. The last thing you do is to transfer control to this block, which is a bit less than the message sent, because you don't want to push a new stack frame into the stack.
So here the only thing that you have to implement in another primitive, okay, you have nativize, which tells the VM or the cheater nativize this method, and then transfer control to, which is the new thing, and it's just written in assembler and those 5 lines of code, so it's not that much. So those are the primitives. Also, we have the dynamic link libraries. Our code is built in something that is called a closure. A closure is a term from algebra, and we say that when an object is related to some other object, if one of the objects is in the closure, the other one has to be. And now we say if one object is in the dynamic link library, the other one which is related to has to be in the dynamic link library. And we extend the concept, and we say full closure, and we say if we want to send a message to some object which is in the closure, the nativization or the native code has to be in the closure. So we found some problems with supersend. Supersend is not trivial. And when we generate this closure, we found that it was hard to detect if the supersend, the method of the superclass, is in the closure. So is object initialized in the closure? Also, we have this is another issue. Is okay, we have object and A initialized. and we want to put B into the closure. How we do detect if B initialized is in the closure? We have to think about that. And we use validators to detect those things. Validator is some Smalltalk solution to this kind of problem. When we are running the code, we check that all those assertions are valid. In the living code, in the living objects, we check that. And I think it's a Smalltalk solution to a problem that, I don't know, is complex. Also, we need to synchronize when we don't have the full closure, we have a partial closure. It's not a closure, but we call it a partial closure. And we have to synchronize the object in the library with the object in the image. We already did that, but the code was written in C. Now we are moving everything to Smalltalk.
So yeah, here what we are showing is when you load this partial closure, you have some objects that will be pointing to objects that are new. So these objects have to be these objects of the DLL have to be in the remember set. So you have to tell each of them to remember that keys in the remember set, to type it, okay? And then after each GC, the GC of the VM on which we are running doesn't know about DLLs, so it doesn't traverse objects that are, it traverses some objects of the DLL, but it doesn't do everything that should do on objects after traversing. So we have to take care of these references to objects from the DLL to objects in the image. We have to update them after each GC, and well, in some cases we have to initialize the references. This also initialize the references when we load the DLL. And finally, we try to test everything we code. We test it, or most of things we code, we test them. And also, when we find bugs, we try to add tests to assert that these bugs are not present anymore in next versions of the VM. So in this case was about a bug we found. We tried to assert that after the GC, all objects in the DLL roots are not marked as traversed, because after the GC they should be left as unmarked.
And finally, we have to extend sends. And this is a typical send. We just send show to Ola, which is a string. And this is handled by the send selector bytecode, a typical class. But we use that. We use under primitive. We send being remember set to Ola, and this is something special. It has no class check, so, and it's in line. It's in line in the final assembler. So we handle that with sending liner. But the new thing is the invoke sending liner. We want to tell an object, okay, invoke this compile method. I want show object show to be used on Ola. That's something that we could do, and something that we are going to use when we want to, when implementing the method lookup, for instance. We have to invoke something without a method lookup, because we don't have any. Here's the implementation, which is very similar to value. So we take the compile method and transfer control to the compile method entry point without the class checks, because we don't want that. So that's more Smalltalk code. That's it. A short one. So. Any question? No? Okay.
Any questions?
No?
I thought in the first part of the presentation that you were trying to take advantage of the 32-bit procedures. We thought about using programming language to do that. So structure.
Sorry, using what?
Local machines.
Okay. Okay. Yeah, but we thought about using SmalltalkVM, but we want to use Smalltalk. Yep.
You mentioned something that have some circle or some code that the server is talking about getting before what challenges are you creating test?
Well, it's like make sometimes sometimes making a test for some situation in particular is like a form of art, because you have to set up everything to get the very instant moment that is failing. So you have to say, okay, I want to have this object here, and I want to have a space that is almost full, and so the object won't fit into the new space. And then I want to test this, but not in any moment, but I want to do it after 2 GCs, because that's in the moment when it breaks. So the challenge is to write the test, to find a way to write the test which is not too much complex. Because many times the tests are complex because of the setup of the situation. This is a really hard part. I think it's the most hard part of writing a test.
Yeah, but I think the more interesting part is not that like writing a test, but to try to understand the issue, to try to detect the actual problem is time-consuming.
Yeah, it's much more.
It's much more time-consuming than writing the test. It's the more interesting because you understand a lot that you haven't understood before. I think that is the very, I don't know, enlightened experience. I don't know.
I have a question. So, just to make sure, the clarification then would be, so instead of running, say, 5,000 tests that don't really test the VM, but you know that they crash the VM sometimes, instead of doing that, like, and of course if it doesn't crash, you're not sure, so you run them again. If it doesn't crash, you're not sure, so you run them again. And after 10 times, you sort of think that maybe it appears to work. So instead of doing that, what you're saying, I believe, is that finding a test that exercises the defect on purpose.
Yeah.
That's the hard part.
Yes, yeah. We try to do that, and it's like a method, like doing science. It's something. It's like you don't want to avoid the bug. We want to reproduce it the most and try to think. What was the last thing I did that it happened to be more often, and exploit that. I know it's very interesting to do that for me. That's it. Leandro?
You might have a few minutes for one more question.
Leandro?
Okay, I already know the answer, but maybe it's interesting.
An answer.
What about documentation?
Yeah, I have. Sorry, but I have a good one, and I want to show you. And it's going to be like probably around here. Yeah, I saw one slide with documentation, and it's important. If you remember, this is the presentation. And here, I don't know if you can see. No, you can't. But here, no. Okay. Okay, I have documentation here, so we removed the documentation there, and probably, well, that's the thing. No documentation at all. Try to. Okay, he answered the question he made. Okay, we are working on a paper. I don't know. That's it. Thank you.